Hello students, welcome back to the supplementary video lectures. So today in this session we will discuss about the stiffness method and in that specifically it is an analysis of frame. In the previous session we have discussed about the analysis of the beam using stiffness method, and as we have discussed earlier also these video sessions are helpful for their additional learning apart from the regular classes. If you have any doubt you can see that video, and you can go through it, and you can along with this you may solve the example which we can do over here. So let me start the analysis of frame using stiffness method. Basically, there are two type of the frame which we have learned earlier using the conventional methods. Also, there is a non-sway frame and sway frame. In non-sway and sway, what is the difference? That non-sway frames are analyzed exactly like we are considering the continuous beams, while in the sway frame there is a little bit difference, as there is a unknown is lateral deflection also. So today, first of all, in this video session, we will see about the non-sway frame, and in upcoming another video, we will see the one practice example of the sway frame. So let me start with the numerical here. We have to analyze this frame using stiffness method. So what we have to do first, like we have considered in case of the beam, what is the first step? That we have to find out the ki. So let me begin with the first step over here. So basically, if we consider the actual figure over here, so how many KIs we have? At A, it is a one rotation. At B, there will be three displacements, and at C, there is another intermediate joint. So there are three displacements. So total number of KIs are seven. Now, if we neglect the axial deformation, so how many KIs are remaining? So let me check. So for these horizontal members, as it is a three members, and two horizontal displacements, so that two will be going to neglect. So if you consider this horizontal deflection is going to neglect, and similarly this horizontal deflection is going to neglect. Similarly for this column BE, the horizontal uh, vertical deflection will be become axial, so that BE will be going to neglect. Similarly, for the CF, the axial deformation, this vertical one will be going to neglect. So here, what is the remaining thing? So here remaining are the nothing but it's a three rotations only. So that is a nothing but it's the same as we have considered in case of the beam. So earlier also we have considered, if you refer the previous one, in which the unknowns are rotation. So we have a three rotation, rotation at A, rotation at B, and rotation at C over here as our primary unknown. Next, that we will represent as a D1, D2, D3, and here we will consider that as a in a clockwise direction only. Next, for this frame, as we have decided, we are restraining the structure D1, D2, and D3. So what is the first step? That we have to find out the AD. And what is that AD? Like we have seen in the case of the beam, AD is nothing but action in the actual structure corresponding to unknown joint displacement with respect to unknown degree of freedom. So with respect to this degree of freedom, can you see over here that with respect to D1, is there any moment at the joint at A? No. So AD1 will be become a 0. Similarly, with respect to D2, is there any joint moment with which is acting specifically at the B? No. So that is also 0. And similarly, at the C, with respect to D3, is there any moment will be acting at the C? So no, it is also 0. So our AD matrix, that is a 0, 0, 0. Always AD and ADL, that is a three rows and one column, which is indicating that three rows, which is a with respect to the three unknown degree of freedom, and there is a always one column, that's a kind of the column matrix. Next, ADL. So ADL is with respect to the friction moment. So we have to find out the friction moment in the individual span. So let me start with the first span, AB. So what is the friction moment? It's a WL square by 12. So here A, it is anti-clockwise, B, it is a clockwise 37.5. Similarly, in the BC, as it is a eccentric load, so both the side it is a different moment, WAB square by L square and WA square B by L square. And last CD, that is at acting at the center, so it is a WL by 8. So it is a 60 and 60, left hand side anti-clockwise, right side clockwise. Now with respect to this unknown degree of freedom, we have to consider the total fixed moment at the different location, and that will be ADL. So first one, if we consider over here, so what is with respect to D1, what is the total moment at A? That is a 37.5. So that is a anti-clockwise, so we have to consider minus 37.5. Second one, with respect to D2, here total moment at a B, there is no fixed moment at a BE because there is no loading. So what is the total summation of the moment? So it is a 37.5 minus 23.44, so it is a 14.06. While D3, with respect to D3, here at the moment at C, that will be 14.06 minus 60, and that is nothing but it's a minus 45.94. So this is our ADL matrix. So again, I will remind you over here that what is the difference between the AD and ADL? AD is nothing but that is with respect to the joint moment with respect to unknown degree of freedom, while ADL is an external resistance structure with respect to the unknown degree of freedom due to the member load and fixed moments. Now, next point if we go, that is a stiffness matrix. So we have to follow three figures. As you aware about it, what will be the size of the stiffness matrix? It will be 3 by 3 because it will be depend on the Ki. So these are the primary definition of the stiffness matrix which we have seen in the previous video session also, that SIJ, there is action in a I due to the unit displacement RJ, that when we are applying the one by one unit displacement at each and every location, whatever moments, as the unknowns are rotation only, so whatever moments will be generated at a different location due to the unit displacement, there is a nothing but the stiffness coefficients. So let me start with the first one, and we will consider d1 equal to 1. D1, we are considered rotation at A, so we are going to rotate the joint A in the clockwise direction. Due to the rotation in the at A, there will be two moments. There is a both will be in the clockwise direction. Near end, which is a moment, is a 4 ei by L. Far end, that will be 2 ei by L. So the total moment at A, that will be first point, our first action, that will be 4 ei by L. Second point, total moment at B, that will be nothing but 2 ei by L. And here at a C, there is no moment because of the rotation at A. So that is will become a 0. So that will be our first column of the matrix. EI is a common 1.33, 0.67, and 0. Second thing is we have to give the rotation at B. Now, when we are considering rotation at B, so that means here, okay, so here we have to rotate this joint in the clockwise direction. So how it is going to rotate? Just you can imagine, right? This joint B is a rotating, so how many member is going to affect? So that will be BA, so that will be going as it is a rotating clockwise, so the deflected shape is like this, that BA and BC is going to deflect, and while this is going to rotate like this. So there will be three members which is connected to the B that will be going to affect it. So here, if we are applying the moment over here due to the rotation at B, so at the near end, at the B, there will be 4 EI by L, while in the far end, there will be 2 EI by L, and all the moment will be clockwise. So with respect to span and with respect to moment of inertia, we have to consider that at the B it will be 4 ei by L, so at A it will be 2 ei by L. Similarly, we have to consider the effect of the change of moment of inertia. There is a change of geometry also. So with this, if we are considering the second column of the stiffness matrix, so what we can consider over here, that first point is moment at A, that will be 2 ei by 3. Second point, at the moment at B, there will be three moment we can see. There is a moment in a BA, BC, and BE. So we have to do the addition of that three moment. So 4EI by 3 plus 4EI by 4 plus 4E 2I by 4. Similarly, moment at C, that will be 2EI by 4. So that is the second column of the matrix, 0.67, 4.33, and 0.5. Similarly, if we go for the same thing, we have to apply in the D3 equal to 1. And in that, similarly, if we try to draw the deflected shape over here, so which member is going to affect due to the rotation at C? That will be member number CB, CD, and CF. So let we consider over here. So this is my member C, joint C. So here CD will be going to deflect like this. BC or CB will be deflect like this, while the CF will be going in this manner. So if we consider the moments, so all the moment will be clockwise, and one by one, if we represent it near end, that will be 4EI by L, and far end will be 2EI by L. Same way, we have to consider the I 2I in the CF, so that will be nothing but 4EI into 2I divided by 3 and 2E2I by 3 on the far end at the F. So again, we will consider one by one 3 point with respect to our unknown degree of freedom. So what is the first point? Like moment at A, which is a 0. Moment at B, that is a 2EI by 4, that is a zero point 0.5 EI. And moment at C, that is a summation of the three moment in the CB, CD, and CF. It is a 4EI by 4 plus 4EI by 4 plus 4E 2I by 3. So it is a 4.67 EI. So this has become our entire matrix. You can check the characteristic of the matrix from this, that it is a symmetric matrix, Sij equal to Sji. Second thing, you can verify also that the principal diagonal, that is always positive, 1.33, 4.33, and 4.67. In any kind of the example, if you can see, stiffness matrix is also having the same characteristics. And if you consider the third point, that when you are finding the determinant of this stiffness matrix, that should be never be zero. If it is a zero, then it is a considered as a unstable structure. So for any stable structure, it should not be zero. Now we already we get the AD and ADL. So this is our equation for the primary unknown, D equal to S inverse AD minus ADL. So this is a S. Based on the stiffness matrix, we can find out the S inverse of it, and that we can put it over here, AD minus ADL, as AD is a 0. Directly we have to just change the sign of the bracket of AD minus ADL, and just we have to multiply the two matrix 3 by 3 into 3 by 1. So ultimately we will get the 3 by 1, which is a 3 rows, which is indicating the our unknown displacements. So that is a 1 by EI 33.04 minus 9.61 and 10.87. You should just go through the matrix multiplication manually or in your calculator or in the Excel, and you can multiply these two matrix and just verify this answer. So what is the indicator of the minus sign? That at the rotation at B, that we have assumed as a clockwise direction, but it is nothing, but it is in anti-clockwise direction. Now we have to use this displacement to find out the unknown secondary unknown, that is a bending moments. So as we have to find out the member and actions, we will consider all moments in the clockwise direction, AM1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. As it is a five member, in each member we have to consider two moments. So we have a total 10 rows, and we have to find out three vectors, AM, AML, AMD. In that AM, there is a member action which we will consider, which whatever member action we have to find out. AML, there is a nothing but it's a member action due to the loading, which we the in which we have to consider the figure which we have considered for the friction moment, and in which we have to follow the sign convention of the previous figure. So if we are considering one by one each and every moment according to the sign, that as we have assumed the clockwise as a positive, so anti-clockwise will be minus. So in this sequence, AM1 to AM10, we have to follow it. So first one, minus 37.5, 37.5, 23 minus 23.44, 14.06, then 16 minus 60, 60, 0, 0, 0, and 0. Plus there is a some AMD over here. Then 33.04 minus 9.61 and 10.87 is our unknown displacement, which we have find out in the as a primary unknown. Now we have to find out the AMD. In the AMD, we have to use the figures which we have considered to generate stiffness matrix. That is a D1 equal to 1, D2 equal to 1, and D3 equal to 1 by 1. So first, if we consider the d1 equal to 1, so in that it is a first figure that we have to use in the first column of the AMD. That is a moment at A is a 1.33, at B it is a 0.67, and remaining all are 0. Because as we are rotating joint A, there is no such effect in the remaining members. So that is our first column. Similarly, second column. So in this, you may refer previous figures also. That is the same. I have just put it over here, and that is a d2 equal to 1, in which whatever moments are shown over here that we have to consider in the second column of the AMD matrix. So that's a 0.67, 1.33, 1, 0.5, then 0, 0, then 2, 1, and again 0, 0 in the CF. Similarly, last step, there is a this one, d3 equal to 1, and we have to consider all the moment, all 10 moments in the sequence. So first 0, second 0, third 0.5, then 4 by 4 it's a 1, again 1, 0.5, then in a BE it is a 0, 0, in the CF that is a 2.67, and last is a 1.33. So we are ready with our this AML and AMD, and that we are going to multiply with a D. So if we are going to multiply it, the two matrix, as it is a 10 by 3, and here it is a 3 by 1, so ultimately we'll get the 10 rows in one column, and that we have to add in the AML. So this is a product of the matrix multiplication. You should calculate one by one. It is a, if you are doing manually also, it is not take much time. It is just a repetitive value. So one by one, each row you should calculate it, and you will get this vector. And ultimately, if you are doing the addition of this, so you will get the final moment over here. So this we have to shown in a form of the diagram over here. So you can just verify it that here it's a 0, second 56.77, that is a plus, second third minus indicating anti-clockwise direction, 20 that is a clockwise, 49 that is anti-clockwise. Likewise, we have to consider all the moment clockwise and anti-clockwise direction first in the our initial figure. Based on this, you can just verify that in the ABs, BC and CD, all moments are hogging. So that we will show all the moment as like this. We have to just connect it one by one to each other. And at A, as it is a hinge, it is a 0. Now if you consider in the BE, so what happened that here, as it is a hogging, but here it's a sagging, so it is going from the plus to minus in the case of the BE. So that is our moment at BE. Similarly, if we are considering over here in the CF, at the C it is a shagging, and at the F it is a hogging. So here again it is going from plus to minus. Above it, we have to draw the span moment. In the AB, it's a UDL, so span moment is a WL square by 8. While in the remaining two, there is a point load, so it is a WAB by L, which is a nothing but it's a positive. So that is our shear force diagram for this frame. So you may compare this entire example also by solving using the slope deflection and moment distribution method. And you may compare that which one you feel easier and what is a and you may feel the numbers with this example and compare it that how this method is a more easier as compared to the previous two. So with this, we are going to end this session. For your any doubts and comments, always I am here. So you may share your feedback in the comment section and personally to me. So thank you so much, and we will meet again for the another one session of the video for the wave frame analysis. Thank you.